Okay, welcome back to our Chapter 8 discussion on angular or rotational motion. And we left off the last video on this slide, which is basically a recap of a lot of the information we've gone over so far. So there are a lot of formulas in this chapter, but they're not really all that new. If we look at angular velocity, for example, this is essentially the same as our linear velocity being equal to delta x over delta t. So we've just translated it into this new terminology for angular motion of omega equals delta theta over delta t. So omega is angular velocity, v is linear velocity. Theta is angular distance or displacement. X is linear displacement, and time is the same. And then we have alpha, which is angular acceleration, delta omega over delta t, just like our linear acceleration a is delta v over delta t. And the relationship, the link between linear and angular is x equals r times theta. So x being displacement, that's equal to r theta. And then that allows us to say, okay, well, if x is r theta, then velocity is r times omega, and tangential acceleration is r times angular acceleration, alpha. And then finally, we have centripetal acceleration, which is equal to v squared over r. And since v is equal to r omega, we could say it's r omega squared over r, and then that simplifies to just omega squared times r. So it may seem like a lot, but a lot of it isn't really new. It's just in a slightly different context. Let's look at an example problem here. We have a carousel that is initially at rest. At t equals 0, it is given a constant angular acceleration, so it's going to begin to increase its angular velocity at a rate of 0.060 radians per second squared. And that's something that I may not have mentioned in a previous video. When we're dealing with any of these formulas, we want to make sure that theta is in radians. Now, frequently angles are measured with degrees, and in fact, sometimes if what we're looking for is theta, when we report our answer, we may actually want to convert these radians into degrees so that we have a better understanding. We can visualize 90 degrees or 45 degrees better than we could visualize a certain number of radians. But when we are plugging them into formulas, we definitely need to make sure we're using radians. And there are 2 pi radians in 360 degrees. So one full rotation in radians is 2 pi. In degrees, it's 360. So we could also say that pi radians is equal to 180 degrees. So just keep that in mind. The velocity is going to increase for a period of time of 8 seconds. We want to know the angular velocity, so that's omega that we're looking for. And we want to know the linear velocity, so that's v, of a child that is located 2.5 meters from the center. So let's begin. Let's start with our definition of angular acceleration. Angular acceleration alpha is equal to the change in angular velocity omega over the change in time. Another way to express delta omega is omega 2 minus omega 1 over delta t. And we want to know the angular velocity. And we know that we are going to start at 0. It starts at rest. This is an unknown. The time is given to us, and the acceleration is given to us. So we can solve this equation for omega 2, the final angular velocity. So that omega 2 is going to equal our alpha multiplied by delta t, and then add omega 1. Except that we don't really need to worry about that because that's 0. So basically our final angular velocity is just going to be equal to our angular acceleration times delta t. So that is 0.060 radians per second squared, and our time was 8.0 seconds. So if we look closely at our units, what's going to happen here is this second is going to cancel out with 1 of the seconds there, and we end up with radians per second. And our the numerical value here, 0.060 times 8, will give us 0.48. So we end up with radians per second here, and that is true, that is accurate. But radians per second isn't frequently the type of unit used to describe rotation. Usually we want to talk in revolutions per minute, or RPMs. If you look at a tachometer in a car or a record player, it's described in RPMs. So although this is technically correct, and we'll leave it there for now, just keep that in mind that frequently we're going to want to convert that radians per second to something like RPM that's more commonly used. Okay, and we also wanted to know the linear velocity of a child that's sitting on one of the horses on this carousel. So that relationship between linear velocity and angular velocity is v equals r times omega. So we just found r to be omega to be 0.48 radians per second. And the radius, the distance from the child sitting on the carousel to the center of the carousel, is 2.5 meters. And so here is where actually I wanted to point out, looking closely at the units. So this is going to end up being a linear velocity in meters per second. So you might be wondering, where did the radians go? And radians are kind of an odd unit. We sometimes write it out so that we just have a placeholder there. But radians are really just a ratio of circumference and distance. And so they're really kind of unitless. We can write out the abbreviation rad for radians as a placeholder where it's convenient. But when it is multiplied by another unit to get a derived unit like this, they just kind of disappear or fade into the background. So the radians kind of go away, and we're just left with meters per second. And the actual numerical value here of 0.48 times 2.5 is 1.2. So if you're traveling on this carousel and suddenly your carousel horse were to break free and go in a straight linear direction, that velocity there would be 1.2 meters per second. Okay, so let's introduce some more terms here. Frequency, abbreviated with an F, is essentially just a way to describe how quickly something happens or repeats. So in this case, we're talking about traveling around in a circle. So frequency is essentially how fast or how many rotations do we make in a given period of time. And so if we take our angular velocity divided by 2 pi, which is in radians the distance of one full rotation is 2 pi, that will give us our frequency. How many rotations do we make in a given period of time? We're taking our angular velocity in radians per second, and we're dividing that by a full rotation to find out how many rotations or revolutions per second. And the unit for frequency is the hertz. And it is kind of a funny looking unit. It is an inverted second, because frequency can be used to describe pretty much anything. Insert kind of a blank placeholder here, per second. So it could be a revolution per second. It could be a number of beats per second. It could be, when we're talking about sine waves, sound waves, the number of waves per second. It's basically anything per second. So that's why it's 1 inverted second is the units of a hertz. And so the inverse of a hertz, if we just invert this fraction, would just be seconds. And so that number or amount of time it takes to make one full revolution in this case is a period. So period, this t is period. And I think t is used here to represent time. We can't use p, that's already used for momentum, so I believe that's why it uses capital T for time, is 1 over frequency. So if you take 1 over 1 per second, then that we just invert the denominator and we end up with seconds. Okay, so here again, I've already alluded to this several times throughout this and previous video, the relationships, the similarities between angular and linear motion. Essentially, when we're talking angular, omega is the new v, and alpha is the new a, and theta is the new x. But if you just basically swap out those variables, the structure of these formulas is the same. The same concepts are true for both angular and linear momentum. So these are our constant acceleration equations. So we had these linear motion constant acceleration formulas that we used to solve problems throughout several chapters. And now we can also solve similar problems involving rotational or angular motion with these angular constant acceleration equations. For instance, example 8.6, a centrifuge rotor is accelerated for 30 seconds. So we can write down our delta t is 30 seconds from rest. So our initial angular velocity is 0 to a final angular velocity of 20,000 RPMs. And we want to know what the angular acceleration is. And then part B will ask how many revolutions does it go through during that period. So I'm almost up on my time limit here, so I will end this video here and we'll solve this example problem starting in the next video.